Hello everyone and welcome back to the channel. Now in today's video we'll be looking at the min-max function for the generative adversarial network. For those of you who already know what a generative adversarial network is and want to kind of know what the min-max function is directly, do skip the first couple minutes of this video. Now to clarify a few things prior to the explanation of the min-max function, the generative adversarial network is a type of neural network just like the convolutional neural network, which some of you may be more familiar with, also known as CNN, and it is located under deep learning, which is a category of machine learning. Now, we really need to kind of understand the whole hierarchy here. It's AI first, and then machine learning, and then deep learning, and then deep learning divides into supervised learning, unsupervised learning, and semi-supervised learning. But we won't be looking at that in this video. And the generative adversarial network is located under unsupervised learning, while CNN is located under supervised learning. Okay, since we kind of understand the whole placement of GAN and the whole scope of AI, let's dive into what GAN really is. So the generative adversarial network, or GANs, are a type of neural network, a type of deep learning model composed of two neural networks known as the generator and the discriminator. Now, they work together in this sort of very unique way where the generator tries to create data that looks like real data, while the discriminator tries to distinguish between the real and the fake data. Now, over time, this sort of adversarial process really leads to the generation of data that's nearly indistinguishable from the real input data. Now, in very, very simple terms, GAN is often compared to a game where the generator is the counterfeiter, and the discriminator is the detective. And with each iteration, both networks become extremely skilled, eventually leading to the generation of highly realistic outputs. Okay, now that we know what GAN is composed of, let's take a look at the whole min-max function. Okay, so this is the min-max function, and here the generator's goal is to output data that is perhaps minimized, to kind of minimize this entire function. So its goal is to minimize the function, while the goal of the discriminator is to maximize the function. Here, the term X represents the real data, and the term dx represents the discriminator's prediction for whether that real data is real or fake. And the term dx ranges from 0 to 1, where 0 means that the discriminator predicts the data to be fake, and 1 means the discriminator predicts the real data to be real. So since the input data is real, the dx term should be 1, and the closer it is to 1, the better the discriminator is. So this is kind of the desired scenario for the discriminator. Now, in the latter part of the equation, the term GZ represents the generated output, or the generated data from the generator, and the term DGZ as a whole represents the discriminator's prediction for whether that generated data is real or not. Now, since the data is generated, the term DGZ, representing the discriminator's prediction for the generated data, should be 0 if we were to have a very good discriminator. So it's ideal for the discriminator to output 0 in this case. Now, let's look at a scenario where we have a very good discriminator and a bad generator. Since the discriminator is very good, the term dx should be 1, since it should be able to correctly identify the real data. Therefore, if we substitute 1 here, log 1 would equal 0, and the entire term kind of just cancels out. Now, the generator is very bad at creating realistic fake images. So the discriminator detects it, and so the term dg should ideally be 0, which when we substitute it, we get log 1, and it's again 0. Now, under this scenario, the whole value of the loss function would be 0. On the other hand, let's look at another case where we have a very good generator and a good discriminator as well. Now, in this case, with a very good discriminator, the term dx should again be 1. So we have log 1, and we know that this is going to be 0. So the first term, this part, equals 0 again. Now, with a very good generator, the discriminator will effectively struggle to predict whether the generated data is real or fake, and this is really important. So we'll make a guess, thus outputting the value 0.5 for the term dgz. As it's not at all sure whether the data is real or fake, and it's therefore making a guess, which has a 50-50% odd. Now, so if we substitute the value 0.5 into this log function, we get log 0.5, which is minus 0.3. And this is kind of effectively this state where the generated data is so good to the extent that the discriminator is making a prediction, a random prediction, is the sort of ideal state for the min-max function, where the generator is so good that it outputs fake data that is so realistic that the discriminator can't even distinguish it. However, the discriminator is still so good that it correctly predicts the real data as real. So very, very simply put, the first part of the equation, this part of the equation, essentially tells us how good the discriminator is, and the latter part, this part, tells us how good the generator is. And this tells us how good the generator is. So the higher the first part, the better the discriminator, and the lower the second part, on the premise that we have a really good discriminator, the better the generator. Now, we can really kind of see that this does align with what we have mentioned earlier. This sort of goal for each of the generator and the discriminator neural networks, that the discriminator is trying to maximize the function, however, the generator is trying to minimize it. We can see that this kind of extrapolation does align with the premise mentioned earlier on. Thank you.